Okay, welcome to lecture here. We'll get started in just a second. We'll continue on with chapter 8, acid and bases. Okay, so we've been talking about acid and bases here in this chapter. So a couple of reminders. An acid is really something that can produce, as we talked about last time, H plus ions in solution. Um, H plus ions, which is the hydrogen ion, which is the same in sort of acid base chemistry as H3O plus. So again, when we see something like H plus or H3O plus, which is the hydronium ion, they are essentially the same thing. So they sort of mean the same thing here when we talk about acid and bases. They're essentially the acidic part of the solution, the H plus or OH minus. So again, you can basically, for each of those, really use them interchangeably, and they are used interchangeably in acid and base chemistry. Um, they are used in the formulas. They're also used in equations sort of interchangeably. So as we talked about last time, wherever I put sort of H plus, because that's typically what I use most of the time, you basically can replace it with H3O plus. Again, pretty interchangeable, the acidic part of the solution. And so an acid is really something that has the ability to produce that. And when we talk about producing that, we're talking about free H plus. So in solution, free H plus ions are basically able to float around. While a base is really something that can produce OH minus, which is hydroxide. So when we talk about bases, that is our OH minus that's being produced. Um, and again, it's the same idea. It's something that really has that ability to produce OH minus in solution. And we're again not talking about OH minus that's attached to anything. It's really just free floating OH minus in the solution, just like the H plus is free floating H plus in that solution. So those are sort of generic sort of definitions of acids and bases. A more sort of general definition of acids and bases is one that most people sort of think about, which is the Bronsted-Lowry definition of an acid and a base. And in a Bronsted-Lowry definition of an acid is a proton donor. So that is something that will donate an H plus. And it's important to remember that it's not just the H that is getting donated there, but it's also the plus part. So it does affect the charge when that happens, either when it's being donated or, as we'll talk about here with a base is something that will accept an H plus. So it does affect the charge, that plus part of it. When you lose a plus, you become more negative. And if you gain a plus, obviously you become more positive in that sense in terms of the charge. So that's always something sometimes people kind of mess up on, is they understand the H part, but the plus part affects the charge. So you want to make sure you keep that in mind. As we talked about as well, there are relationships that occur in that Bronsted-Lowry definition of an acid and base, where the acid on one side, like we have here at the very top, this acid here on our left-hand side, is related to somebody on the product side, and that is what is known as the conjugate base. So those two things are related to each other, just like the base on one side is related to the conjugate acid on the other side. So the relationship between these two things, as we talked about last time, is simply that H plus relationship, and it's one H plus only. So the relationship between both of those things, the acid and its conjugate base, or the base and its conjugate acid, is just a difference of one H plus, and it can only be one H plus at a time. And that is because the acid will essentially send its H plus over to the base. And when it does so, the base accepts an H plus, the acid loses an H plus, and again, their partners on the other side are our conjugate bases and our conjugate acids. So that's an important thing. Again, only one H plus difference. And that's the only difference that you could have when you're looking for an acid conjugate base pair. As we saw in some of these examples here, HS minus, when it would lose an H plus, it becomes S2 minus. Again, when it loses the H, we lose that, and the plus makes this one more negative, which is how we get to our -2. So again, one H plus at a time difference, the only difference that there can be in order for those things to be related to each other. Any questions on any of that there that we talked about, I think, last time? Okay, so I think we also kind of finished up talking about writing either a conjugate acid or a conjugate base. And again, sometimes it's good to think about those things sort of backwards. So as we sort of, I think, talked about last time, if you're asked, for example, to write the conjugate acid for something, you want to think about backwards that the conjugate acid is related to the base. And the definition of a base is something that will accept an H plus. So that's how you know you should put on the H plus in that case. And backwards as well, if you were asked to write the conjugate base, if you go all the way back over, it is related to the acid, and definition of an acid is something that will donate the H plus. So sometimes it's good to think backwards, because sometimes they will not tell you, hey, this is an acid or a base. They will ask you just to perhaps give the formula for the conjugate acid or conjugate base. So if you kind of think about it backwards, it sometimes helps you understand what you should be doing. Really, the only thing you should be doing has to do with the 1H plus. So that's the important part to remember. The main trick is to know, should you put the H plus on or take the H plus off? And again, thinking about it sort of backwards oftentimes will help you sort of figure that out. All right, any questions on any of that stuff there? Okay, so I think where we left off was here, a little bit about acid strength. So when we do have an acid, and by the way, this is just a generic sort of formula. I think we talked about it last time for an acid. So this is just a generic acid. And in the forward reaction, we do produce H3O plus and A minus, which again is our conjugate acid and conjugate base. But again, in certain cases, those products can then come back together and form our reactants. And as we can see in this case, our products will become our reactants and will form that. In this case, we get this reversible reaction like we talked about in a previous chapter, which is an equilibrium. And we typically see this for a weak acid, and it could even be a weak base. So that reversible reaction is typically for something that's a weak acid. For example, hydrofluoric acid, HF, is a weak acid. When it's in solution, it will break apart into H plus and F minus. But for the most part, this is what we have going on in the solution. We have the acids still together, but we do produce a little of these guys. Kind of like what we talked about with electrolytes here. This is basically a weak electrolyte, this weak acid. A weak base is also a weak electrolyte. And that's different than, say, a strong acid like HCl, which is hydrochloric acid. It goes 100% towards the product side. And when it's in solution, it 100% breaks apart into ions. You have none of these guys still left. And that's why this is really considered a strong acid like HCl, because as soon as it goes for a swim, it produces a lot of free H plus. And that's basically, again, your definition of an acid is that H plus. And that's different than in the HF case. In the HF case, when it goes into solution, this weak acid will mainly stay together, but produce a little bit of this guy. So still technically an acid because it has the ability to produce H plus or H3O plus. But unlike a strong acid, it's not going to produce anywhere near the amount of free H plus, and thus is a much weaker acid in that particular case. So again, if that forward reaction predominates, maybe not just a giant arrow like this, we do get a strong acid, and again, it's sometimes referred to as being completely ionized or completely dissociated. And those are fancy words for it completely 100% breaks apart into ions. So again, none of the whole unit of the acid is still there in a strong acid. You have pretty much all ions, and again, you're producing a good amount of free H plus, and that's going to make it a pretty strong acid. If the opposite is true, and really sort of the reverse reaction predominates, like we have in like our HF example, really this would be a reversible reaction, and we do get this sort of weak acid that is formed in this particular case. Now, there is sort of a relationship between, say, acids and bases and their conjugate partners. And the relationship that we see are opposite relationships. And that is, if we have a strong acid, it has a relatively weak conjugate base. So they're opposites in terms of their relationship. So if something is a strong acid, its conjugate base is relatively weak. So for example, HCl breaks apart into H plus and Cl minus. This is a strong acid. Its conjugate partner is relatively weak. And this would be his conjugate partner base. And that's opposite if you had something like HF that we're talking about. This is a weak acid. Its conjugate partner, which would be the F minus in this case, is relatively strong. And again, it's sort of that opposite relationship. So if something comes from a strong acid or even a strong base, its partner on the other side is relatively weak. If something comes from a weak acid or a weak base, its partner on the other side is relatively strong. Truth be told, for our class, not a really important sort of thing to truly understand. If you go on and take more chemistry somewhere, it is an important sort of idea to remember. But just for us, that's sort of the relationship that happens. These are some strong acids: sulfuric acid, hydrochloric acid, nitric acid, perchloric acid, HBr, which is hydrobromic acid, is also a strong acid. HI is also a strong acid, hydriodic acid. So these are some very common sort of strong acids. Some weak acids, which are very common. HF, as I sort of put there. HNO2, which is nitrous acid. HCN, acetic acid, which is basically vinegar. That's another sort of weak acid as well. So those are some weak acids. As you can see here, something like sulfuric acid is what is referred to as a diprotic acid. So if we have something like HCl, HCl is H plus and Cl minus, hydrochloric acid. It pretty much can only give away one H plus. So this is what is sometimes referred to as being a monoprotic acid. And really, we're talking about this guy over here. Again, because it only breaks apart into one H plus. Something like sulfuric acid, which is H2SO4, can lose two H pluses. And by the way, they do come off one at a time. So the first thing that would happen is the first H plus would come off, and then the second H plus would come off. They actually don't come off one at or both all at once. They do come off in what is sometimes referred to as a stepwise fashion. So, and that's why earlier when we were talking about sort of conjugate acid and base pairs, for example, erase some of this here, right. So, for example, what happens in something like phosphoric acid is the first thing that will happen is H2SO4 will drop the first H plus off, and you get HSO4 minus, and then that HSO4 minus will drop off that second H plus and make sulfate. And that is why when we look at this guy, which is sulfuric acid, and HSO4 minus, they are partners. And when we look at HSO4 minus and SO4 2 minus, they are partners. But if we look at going from there to there, they are actually not partners. Again, that is more than one H plus difference. So sometimes we just look at the overall reaction here, and we sometimes think that perhaps they both just sort of pop off at once, and they actually do come off one at a time. Yeah, so in terms of this would be This guy here would be our acid, and this would be our conjugate base, if that was your question. And actually, in this second example, this would be an acid, and this would be its conjugate base for the second guy in that particular example. This guy here, though, is also something that we talked about last time as well. It's amphoteric, which means it could act as an acid going this way, like we have it written there. It could also pick up the H plus and go backwards to here. And that's why it's a partner to both of them, because it could act as an acid or a base in that particular case, because it's amphoteric. And so, yeah, but the way these two reactions are written up here on top, they're on the left there, they're both acting as acids in that case. And that guys on the other side would be their conjugate bases. And again, this guy has the ability to kind of go both ways, either lose another H plus or gain an H plus. And again, that means it's amphoteric. And they do come off, like I said, one at a time. And it is much easier to pop off the first H plus. As soon as you pop off the first H plus, as you can see, you end up with something really with a negative charge. And you're trying to get rid of something that's positively charged. So that negative positive charge, it really holds it a lot tighter and it makes it harder to get off the second one. In fact, in most cases, most of the H plus that comes off is the first H that comes off of that. The second one is not very much. It's very super small usually. That second amount of H plus comes off. So a majority of all the H plus that usually comes off is that first one. And again, this is what is sometimes referred to as a diprotic acid, diprotic, because it basically can lose two H's, two H pluses. And there's things that are sometimes referred to as polyprotic or triprotic acids, like phosphoric acid, which is H3PO4. It can basically drop off three H pluses. And in this particular example here, this is again what would be referred to as a triprotic. Tri for three, protic for proton. It basically has three protons that it can donate. Question on that there? Okay, so let's see here. Water, as we talked about, is an amphoteric substance. And again, a reminder, as we talked about just a second ago and last time, an amphoteric substance is really a substance that in certain situations can act as an acid. In other situations, it can act as a base, which means it really has the ability either to accept an H plus or donate an H plus. So it can really do both along the way. And water is an example of that. So the first one here is water acting as an acid, which means the water here would donate its H plus over. When it does, the NH3 becomes NH4 plus, and we produce OH minus in this particular case. Again, our partners here is water is our acid, OH minus would be our conjugate base, and our NH3 in that first example is the base. The NH4 plus would be our conjugate acid in that particular case. Now, we could take water with HCl, and in that particular case, water is going to act as the base, and it's going to accept the H plus. And when it does, it will form H3O plus and Cl minus. So in that particular case, the HCl is the acid, the Cl minus is the conjugate base, and the water here in the second example is the base, and the H3O plus is its conjugate acid. So again, water is basically amphoteric. It can act as an acid and base, and it can even act with itself, which is sometimes referred to as the autoionization of water. In this particular case, one water is acting as the acid, the other one is acting as the base, and that's essentially what's going on in water all the time. You got this sort of acid-base reaction that's going to occur. So if we say this guy is our acid, he's going to donate. This would be our conjugate base. And if this guy was our base, whoops, this guy here would be our conjugate acid in that particular case. So water, again, can pretty much react with itself. It reacts with itself in sort of a weak electrolyte way, which is why we have these arrows going in both directions. And it does set up an equilibrium. And when it sets up that equilibrium, we get an equilibrium constant and a relationship that's important for water. And that is what is sometimes referred to as Kw. So Kw is the concentration of H plus or again, you can use H3O plus times OH minus concentration equals 1 times 10 to the minus 14. When we put those little brackets, that means concentration. And we were pretty much talking about molarity here. So we're talking about moles per liter when we figure out the concentration. So the H plus concentration times the OH minus concentration equals 1 times 10 to the minus 14. That is a constant for 25 degrees Celsius. Pretty much most of the classes you take, that's the number that you'll use. So you always have that number available to you. And it's always that 1 times 10 to the minus 14. The relationship that happens between these two guys, it's an opposite relationship. So as the concentration of H plus increases, the OH minus part decreases, and vice versa. If the H plus concentration goes down, the OH minus concentration goes up. So basically, as one goes up, the other goes down, and it goes back and forth. And we can use KW to figure out the concentration of the solution in terms of the acid part and the base part. So when we look at these two things, the H plus concentration is really the acid part, and the OH minus is the base part of the solution. And you could calculate both of those things and figure out, is the solution acidic, basic, or neutral, by doing a pretty simple sort of calculation, which is what we see on the bottom. The H plus concentration is equal to 1 times 10 to the minus 14 divided by the OH minus concentration. Or if you want the OH minus concentration, it is 1 times 10 to the minus 14 divided by the H plus concentration. It's really the same calculation regardless of which one you're given. And what we could do with those two things are, if we have the H plus concentration and it's larger than the OH minus concentration, so the acid part is bigger than the base part, the solution will be acidic. If we calculate and the OH minus part is bigger than the H plus part, then the basic part is bigger than the acidic part, and the solution would be basic. If they are dead on each other, which means at that point it would equal 1 times 10 to the minus 7 molar, then the solution would be neutral. So we could actually do these calculations here and compare the two numbers, and whichever one is larger, either the H plus one is larger, then it's acidic. OH minus one is larger, it is basic. Very important in this part of the calculations here as we wrap up this chapter in the calculations. You definitely, one more time, definitely want to make sure you're using your exponent buttons. If you are still not using your proper exponent buttons, you will find yourself pretty far off on these calculations. So make sure that when you type these things in, you do use that exponent button on your calculator. Any questions on that? All right, so let's try some here. All right, we have 4 different solutions. So we're looking for 4 different answers. So if you're given the H plus, what is the OH minus? If you're given the OH minus, what is the H plus? And for each of these solutions, separate solutions, is it acidic, basic, or neutral? So take a couple minutes here. Make sure you get your calculator working right. Again, make sure that you do use your exponent button. So you should have 4 different answers and 4 answers of, is it acidic, basic, or neutral? So take a couple minutes and then we'll go through it and see what you end up with. Okay, so let's take a look and see if we're getting hopefully the same answers. So, regardless really of which one you're given, it really is the same calculation. You're just going to take 1 times 10 to the minus 14 and divide by what you're given. So, our first one, we were given the H plus concentration, which is 3.4 times 10 to the minus 4 molar. And we're looking for our OH minus concentration. So that would be our KW, which is 1 times 10 to the minus 14. So you always have that number. We want to divide it by what was given to us, which is 3.4 times 10 to the minus 4. And when we do that, we want to go 1 exponent button minus 14 divided by 3.4 exponent button minus 4. And it looks like we end up with something like 2.9 times 10 to the minus 11. Since this is a concentration, we would want to put molarity at the end of that. And again, a reminder, when you put this in, you would probably want to hit 1, your exponent button, your negative button, and 14, your division button, and 3.4 exponent button, negative button, and 4, and hit equals. You hope we should get there. So again, you want to make sure that you are using your exponent button. Usually you could find yourself front number looks okay, back number not so much. And again, that's usually the way you're punching it in. So make sure you try to do it this way. Now that we have the OH minus concentration, we can compare the two concentrations. And in this particular case, if you compare it, the H plus concentration is actually bigger than the OH minus concentration, which means that the acid part is bigger than the basic part and it would be acidic. Now, sometimes people get confused on that part. They go, wait a sec, that's 11 and that's a 4. How could this guy be bigger? Remember, the negative here is really important because the top one, which is the H plus concentration, is really 0.00034. The OH minus concentration is 0.0000000, and maybe one more if I didn't miscount there. Something like this, I think. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you can see again, when you have a negative exponent, the smaller number is actually the larger number in terms of magnitude. So this guy is much larger because the guy with a minus 11 means you need to put 11 or 10 zeros in front of it. Question on that calculation there. Okay. The next one that we have is they also gave us the H plus concentration is 2.6 times 10 to the minus 8 molar. Again, pretty much same calculation. We're going to do our OH minus equals our 1 times 10 to the minus 14, which is a constant, divided by 2.6 times 10 to the minus 8. So in this particular case, we end up with 1, again, exponent button minus 14 divided by 2.6 exponent button minus 8. And we do end up with something like 3.8 times 10 to the minus 7. Again, here, this would be molar. And want to make sure that when we punch these in, again, you want to make sure you use your exponent button. So a reminder again, when you do 1 exponent button, that puts up a 1 and an E on a lot of calculators. That E stands for the times 10 part. So you shouldn't be hitting the multiplication part button or anything like that, inverse log or anything. And you just would hit your negative button and 14. You then hit your divide and 2.6, same deal, exponent button and negative button and 8 and hit equals. So you want to make sure when you punch those things in, it will look something like this in most cases on your calculator. And again, when you see that E, that represents the times 10 part. So you don't have to hit the multiplication button. If you are, you will find yourself off and stuff like that. So you want to definitely make sure that you hit it with your exponent buttons and stuff like that. All right, on this one here, we got an OH minus concentration that's 10 to the minus 7. A H plus concentration is to the minus 8. So in this particular case, the OH minus is actually greater than the H plus concentration. And that would make this guy a basic solution. Questions on that? Again, if you're finding yourself off in terms of this number, it's how you're punching it in. I could probably almost guarantee it. So make sure, again, you use that exponent button. Don't do anything extra. A reminder, you shouldn't be using anything like your second or shift button. And you shouldn't be using like your log button, inverse log, or any of those things when you type it in to your calculator. Also, a reminder as well, if you happen not to have one of those two exponent buttons, but you do have maybe a newer calculator that has this 10 to the n button, as we talked about many times in this class, you need to make sure that you put parentheses around all your numbers. So if you have that calculator, you got to put parentheses around all the numbers. Otherwise, it will do the math wrong. So keep that in mind as well. All right, questions on the first two there. All right, let's try this next one here. This next one, they gave us the OH minus concentration equals 6.2 times 10 to the minus 9. Same deal. It really is the same calculation. So in this case, the H plus concentration is going to equal 1 times 10 to the minus 14 divided by 6.2 times 10 to the minus 9. Again, putting it into your calculator, 1 exponent button, negative button, and 14 divide button, and 6.2 exponent button, negative, and 9, and then equals. And if you do all that good stuff there, you will end up with something like 1.6 times 10 to the minus 6. Again, this would be molar because it is a concentration. And that would equal our H plus concentration in this case. So again, at this point, we want to compare the OH minus, which is the basic part of the solution, to our H plus concentration, which is the acidic part. And again, in this case, we see that our acidic part is to the minus 6, which is a larger number than to the minus 9. So in this case, the H plus concentration is greater than the OH minus concentration, which means the acid part is bigger than the basic part. And this solution here would be acidic. Question on that calculation there. Okay, then last one in this group here was OH minus is 8.1 to the minus 3. So again, we want to approach it the same way we've been doing. And kind of the nice thing is it's really the same calculation. So here the H plus concentration would equal our KW, which is 1 times 10 to the minus 14, divided by 8.1 times 10 to the minus 3. Again, we want to put all this in like we've been doing. 1 exponent button minus 14 divided by 8.1 exponent button minus 3, hit equals, and should end up with 1.2 times 10 to the minus 12. Again, we'll put a big M there because we are looking for concentration. Now that we have both of these numbers, we want to compare them. And we do see that the OH minus is to the minus 3, which is a much larger number. And that means that our OH minus in this case, our base part, is bigger than our acid part of the solution. And this guy should be basic. Question on any of those 4 there. All right, why don't you try another one here that you got? Forget what it's asking. So in this case, let's just calculate the OH minus concentration. So calculate the OH minus concentration and see what you come up with. Okay, so on this particular one here, same sort of approach we've been doing. So again, this is that Kw, which is our H plus, and our OH minus, which equals 1 times 10 to the minus 14. So here we're looking for the OH minus. So that would be our Kw, which is this number here, divided by the number they gave us. Again, we want to make sure that we do use our exponent button. And we're going to go 1 exponent button, negative 14, and we're going to divide it by 2.8 exponent button, negative 5, and it looks like maybe a 3.6 times 10 to the minus 10. Looks good. That looks like what we see in our chat box there. So we want to compare. So our H plus concentration was 10 to the minus 5. Our OH minus concentration is 10 to the minus 10. Again, the smaller negative number for the exponent is going to be the larger number. So that does mean in this case that H plus is larger than the OH minus. So the acid part's larger than the base part, and the solution would be, again, acidic. Question on that particular one there. Okay, so we use Kw to calculate either the H plus concentration or the OH minus concentration, depending on which one they give you. And like I said, it is pretty much the same calculation regardless of which one they give you. The key part, again, is you just want to make sure how you enter that in is really important. And remember, again, that idea as we talked about with the negative exponents, again, our smaller number is going to be our larger number. And that's usually what people sometimes get wrong. Okay. So we'll skip this one here and we'll go into the pH scale. So the next thing we're going to talk about is the pH scale. And the pH scale is so how do you know it's acidic or basic is basically in a solution, there's two parts. There's basically the H plus part, which is really the acid part. So in this problem here that we were skipped, we'll just go back and do it here, and this will answer your question, hopefully. So in this particular solution, the H plus concentration is 1 times 10 to the minus 9. The OH minus part is really the basic part of the solution, or the base part of the solution. And that's what we're trying to find here in this particular problem. So if we did this calculation to find the OH minus, it would be 1 times 10 to the minus 14 divided by 1 times 10 to the minus 9. Again, using our exponent button, we want to make sure we punch it in correctly. We should get something like 1 times 10 to the minus 5 molar. And what that means is the OH minus, or the base part of the solution, is 1 times 10 to the minus 5. So what we want to do is compare the acid part of the solution to the base part of the solution. And if the acid part, which is the H plus part, is larger than the OH minus part, it is going to be acidic. If the OH minus part is larger than the H plus part, it will be basic. And if they equal each other, it would be neutral. And that would be neutral. So again, when we compare these numbers, the negative exponent is really important because, as I talked about before, if we sort of wrote, for example, the H plus concentration out in decimal form, what that would be is 0.00000001234567 and 8 in terms of its concentration, versus this guy here, which would be our basic part, which would be 0.00001. And again, we can see that the one with the smaller number is actually the larger part. So in this particular example here, the OH minus is larger than the H plus. So this solution would be basic overall in terms of this. And by the way, a good point to say right now is that when you are asked that question, is a solution acidic, basic, or neutral? Sometimes people go, this solution is acidic and this solution is basic at the same time. So it can't be that. It has to be one of those three answers. Either the solution is acidic, either the solution is basic, or the solution is neutral. It can't be all three at once or two things at once. And it's sometimes very common that people will go, I think it's acidic here, and I think it's basic here for the same solution. And we'll see why that happens here when we talk about pH. Other questions on that before we continue on then? Okay. So then let's talk about the pH scale. Another way that we measure acidity in a solution is the pH scale. And the pH scale really does run from 0 to 7 to 14. And pretty much below 7 to 0, there is acidic. Above 7 to 14 is basic. And when we hit 7 dead on the nose there, it is neutral. And you may ask, well, why is 7 on the nose neutral? It's because when we have something that's neutral, the H plus concentration will equal the OH minus concentration. And they both will equal 1 times 10 to the minus 7, which when you calculate it will give you a pH of 7 on the nose, is basically what neutral means. It is technically 7 on the nose neutral. Anything above 7, a little bit above 7 is slightly basic. Anything a little below 7 is slightly acidic. Some people have a little variation on that, but to keep it simple for us, technically speaking, dead on 7 is neutral. If it's not 7, then it's either going to be acidic or basic in that particular case. To calculate the pH of a solution, we use this equation here. The pH is equal to minus the log of the H plus concentration. So since we're talking about calculators, let's talk about how to properly punch this in. If you have a display calculator, so if you have a display calculator, you punch it in exactly the way it is written. You hit the negative button, not the subtract button. You hit the log button, and then you type in your concentration using your exponent button. If you have a non-display calculator, for this calculation and everything else we're going to talk about for the rest of the chapter, you need to work backwards. You need to start with the concentration or the number. You then need to hit the log button, and then you need to hit the positive negative button. If you're not sure if you have a display calculator or a non-display calculator, which is probably a big question, right? So you hit the log button. If it says log, congratulations, you have a display calculator. If it says error, congratulations, you have a non-display calculator right there. So if it says error, you have that guy. If it says log, when you hit the log button, you have a display calculator. So that's the way that you want to punch these in. And again, you definitely want to make sure that you use their exponent button when you're punching these guys in so that you end up with the right answer when it's all said and done. So the pH is equal to minus log of the H plus. Again, you can substitute this in as minus the log of H3O plus. Same thing, same calculation. So so you just want to put in minus log and then just the number. So 1 times 10 to the minus 14 or whatever it may be, you would put that in. All right, so let's take a look here. Let's talk about sig figs though, and significant and pH. When you calculate the pH, the number of decimal places in your pH value equals the number of significant figures in the concentration. So the number of sig figs in your concentration number is how many decimal places you should put in your pH number. Not significant figures, but decimal places. So it is sig figs to decimal places when you're doing that. So let's just try one here and make sure everybody gets the right pH. So calculate what the pH is here of a solution that has a concentration of 1 times 10 to the minus 5, and do it to the right number of significant figures and see what you come up with. Okay, so let's take a look. So again, we're going to use our pH equation, which is the pH is equal to minus the log of the H plus. So that means it's minus the log of 1.0 times 10 to the minus 5. So again, if you have a display calculator, you're going to hit the negative button, not the subtract button, the log button, and then the 1 exponent button, negative button, and 5. So negative log 1 exponent button, negative button, and 5, and equals. And it should get you 5. Let's just start with that. 5 is the pH. Any questions on how to get that? Again, if you have a non-display calculator, you need to go backwards. You need to go 1 exponent button, -5, hit the log button, and then make it positive. Now, what should the answer be here in this particular case? So let's talk about what the right answer should be. So we have 5. And should it be 5.0? Should it be 5.00? Should it be 5.000? So when we look at the concentration in this particular case, it is 1 times 10 to the minus 5. This has two significant figures. So two significant figures means that I should end up with this guy, 2 decimal places. So not 2 sig figs to 2 sig figs, not 1 sig fig in this case, and definitely not that many. So the number of significant figures in your concentration is how many decimal places your pH value should have. So the right answer here should be 5.00. We also will know that the pH here is less than 7, which means that this solution should be acidic. Again, less than 7. And we'll get to your question in like in 1 or 2 examples. We'll get to your question on that. Yeah. Any questions on that so far? Okay, so let's try a couple here and see what you come up with. These are 2 different problems. So one is what is the pH in both of these? And also, is it acidic, basic, or neutral? So why don't you figure that out? So take a couple minutes here, figure out the pH of this solution, pH of this solution, and are each of those acidic, basic, or neutral? Okay, so let's take a look here. So we'll start with number one. We want to find the pH. So again, that is minus the log of the H plus concentration. So we do have the H plus concentration given to us. So we could go right into here. So this would be minus the log of 2.1 times 10 to the minus 5. Again, making sure to use your exponent button, negative log button, 2.1 exponent minus 5. Going to give us a pH of 4.68 would be the correct answer here. Again, in terms of significant figures, our concentration has 2 sig figs. Gives us, again, not two significant figures, but 2 decimal places here. So 2 sig figs gives us 2 decimal places in this case. That gets us a pH that is less than 7. So less than 7 would be acidic in this particular case. Any questions on number one there? Now, number two, we are looking at an OH minus of 5.9. 5.9 times 10 to the minus 8 molar. And remember that our pH is minus the log of the H plus, and this is not the H plus. So we cannot go right into that to get the pH. We do have to use KW like we did before. So our H plus is 1 times 10 to the minus 14 divided by 5.9 times 10 to the minus 8. And that will get you we'll call it 1.7 times 10 to the minus 7 molar. Now, this is the H plus concentration, so we can go into here. So the pH would then be minus the log of 1.7 times 10 to the minus 7. And gives us a pH of 6.77 as our pH in this particular case. And that also happens to be below 7. So this would be slightly acidic. Now, if you went straight in to this equation here, and you went right into it with the 5.9 times 10 to the minus 8, you would have got 7.23. And all would not be lost per se, because although you did not calculate the pH, you calculated what is known as the POH, because this is the OH minus concentration. And that would not necessarily be such a bad thing, because there's a nice relationship between pH and POH. It equals 14, which means that the pH in this case would be 14 minus 7.23. And that brings you right back to where we started from here. So if you did this, A, it was wrong for this question, but B, you were just like 3 slides ahead, and you actually calculated, though, something known as the POH. And sometimes, as you can see, it's maybe sometimes faster to do that and subtract 14 to get to the pH. You could also do it with KW like we did up here, and hopefully this will show you. Again, you could do it either way. They both will get you to the right answer, the same answer really, just depending on rounding. So, you go either way on that, the POH. Now, this is also where people sometimes run into problems, because they calculate something like the POH and go, oh, that number is above 7, so it's basic. And then they look at the pH and go, that number is below 7, it's acidic. And before you know it, like I said earlier, they are given both answers for this solution. Again, this solution cannot be both acidic and basic. It is only acidic in this case. And when you're trying to determine if it's acidic, basic, or neutral, you should always look at the pH. That is usually the scale most people have in their head. The pOH scale, as we will see, runs opposite. So the pOH scale also runs 0 to 7 to 14. But on the pOH scale, below 7 is basic, above 7 is acidic. So it runs backwards than the pH scale. So most people don't have this scale in their head. Most people have the pH scale in their head. So I would stick to just looking at the pH if you have it to determine if it's acidic, basic, or neutral. Question on that calculation there. Okay. So as the power of 10 increases by 1, the pH goes, changes by 1 as well. So 1 times 10 to the minus 3 is a pH of 3. 1 times 10 to the minus 4 is a pH of 4. 1 times 10 to the minus 5 is a pH of 5. So as we go 1 power of 10 up, we see that the pH also increases up. By the way, none of these are negative. They're just PowerPoint. And by the way, if you have the H plus concentration, that is 1 times 10 to the whatever that exponent is the pH. But if it's not 1, then you should punch it in your calculator. As the H plus concentration increases, the pH goes down. And again, that's because as the H plus goes up, OH minus goes down, and vice versa, as we talked about earlier. So what happens in a situation where the H plus increases, that means there's more H plus in the solution, less OH minus, and that means that the solution in terms of the pH scale will head more this way. And remember that on the pH scale, again, below 7 is acidic, above 7 is basic on the pH scale. As you go from 7 towards 0, it becomes more acidic as you head towards 0. As you go from 7 towards 14, it becomes more basic as you head in this direction. So 7 is sort of your center point there, where it's neutral. As you go away from 7 in both directions, it becomes more acidic or basic, depending on which way you're going. Any questions on that there? So I think we got your question about that. So to answer your question, hopefully we got it there. You could go either way on that, as we were talking about. Now, how do we measure pH? There's a couple of different ways we could do pH. One very common way is to use a pH meter, like what we see there on the left. pH meter is basically an electrode. You stick it into the solution, and basically it does a little voltage type deal, but basically it measures the free H plus concentration that's floating around that solution. So as you stick it in there, it's technically measuring the free H pluses that are floating around. And the nice thing about a pH meter, as you can see here, it typically will give you a nice digital display about what the pH is. Other ways we can do this by pH paper, just sometimes referred to as pH paper. And pretty much you dip it into the solution. It has like a little kind of key. You try to match up all the colors, and it will give you it's a pH of 1, 2, 3, 4, whatever it may be. If you've ever done any type of pool care or anything like that, there's little kind of pool strips that you put into the water. It kind of does the same thing as what you see here. Obviously, the pH meter is much more accurate. It gives you a much better number. This guy is kind of like an estimate on trying to find the right color scheme as to what the pH may be. We also maybe talked earlier as well, we use litmus paper as well. It doesn't really measure pH, but again, it will tell you if the solution is acidic or basic. And typically, if you take litmus paper and it turns red, it means the solution is acidic. Again, will not tell you the pH, but it will tell you that the solution is acidic. And if it turns blue, typically litmus paper means the solution is basic. Again, won't really tell you the pH, but will give you an idea as to whether or not that solution is acidic, basic, maybe even neutral in some cases. Here is the pH scale. And as I mentioned, this is the one you really should sort of look at. That is typically the scale most people have in their head. That's 0 to 7 to 14, as we saw. Again, as you can see here, below 7 acidic, basic above 7, and 7 is our neutral. So we got things like sodium hydroxide, which is a strong base. It's up there in the 14 range in that molarity. ammonia, which is also a weak base. Down here, we got like hydrochloric acid, stomach acid, vinegar, which is acetic acid. Pure water is a pH of 7. By the way, if you take non-pure water, like tap water, and you get the pH of it, yeah, it'd probably be in this range, believe it or not. It's usually pretty acidic. And that's because, especially tap water, if you take it and you kind of leave it out, as you leave that water out, it picks up CO2 from the air. And basically, you make a little carbonic acid, and that's going to increase the amount of H plus in that solution, that water, and it makes it usually slightly acidic in a lot of cases. Sometimes people are surprised when they take like the pH meter and they put it into some tap water and they see it's kind of a pH of 5-ish, 4-ish in that range, depending on your pH meter. And again, it's because it collected a lot of this sort of CO2, made actually an acid sitting in that water, and again, kind of made more H plus, which would lower the pH in that particular case. So we sort of jumped the gun a little bit earlier here, but again, a similar measurement to pH is pOH. The name actually tells you what you need. pOH means I need the OH minus concentration. pH means I need the H plus concentration. So the name itself actually tells you what you need. And as we talked about before, the nice relationship between those two is what we see here. The pH plus the pOH equals 14. This sometimes allows you not to even need to use the KW expression, or you could, like we saw in the previous one. So it gives you some different ways to approach some of these problems. Another couple of calculations which are important, we'll add here. If you are given the pH, from the pH, you could actually get the H plus concentration. And to get the H plus concentration, you take the inverse log of the minus pH. Now, after a lot of people at this point, how they've been putting in exponents, maybe up to this point, this is actually where you use these buttons on your calculator that you shouldn't have been using before. When you hit inverse log, that usually puts the 10 and a caret up. And then you go negative pH. On most people's calculators, you need to hit that second button top left, shift button top left, and the log button. Because usually on most people's, their log button looks like this. So shift and log, again, how a lot of people have been doing scientific notation, which is why you should not be doing scientific notation this way, because now you're doing it to actually do the calculation. So shift log gives you that 10 in the caret, minus, make sure it's not the subtract button, but the negative button there of the pH. You can also do the same calculation with pOH. From the pOH, you could get the OH minus concentration, and that is the same calculation, the inverse log of the minus pOH. Again, when you do that, that's a 10 and a caret on most people's calculator, and you want to do the negative pOH in that case. So those are some really important sort of formulas. It gives you a variety of ways that you could do that. So we have our pOH formula, our pH formula, getting our H plus from the pH, getting our OH minus from the pOH, and we could add our KW to that as well that we saw earlier. Again, you could use any combination of these guys. And again, if you use them correctly, they all should give you the same answer along the way. So, it does give you sort of a variety of ways you can maybe solve some of these problems. Any questions on that there? All right, let's try some of these calculations to make sure. So what do we got going on here? All right, so why don't you try these? Again, two separate problems. Let's calculate the pH, the pOH for each of these solutions. And while we're at it, let's also calculate if it's acidic, basic, or neutral. All right, take a couple of minutes. We're looking for either, actually we're looking for both pH and pOH for each of these. And is it acidic, basic, or neutral? So see what you come up with. Make sure you can punch these in correctly in your calculator. Okay, so let's take a look here and see. So again, as we just saw, we had a variety of ways we could kind of solve some of these. In this particular case, we are given the H plus concentration. So since we're given the H plus concentration, we could go right into our pH, and that is minus the log of the H plus, which would be minus the log of 3.6 times 10 to the minus 9. And that would get you 8.44 as our pH. Again, here you do have a variety of ways. You can use KW to get the OH minus, but probably the easier way would be at this point, the POH would equal 14 minus the pH. So that would give us 14 minus 8.44. And that should get us a POH of 556, it looks like. First off, any questions on those two answers here for the first one? Now, we do want to compare, or we do want to figure out, is it acidic, basic, or neutral? So again, you want to look only at your pH value here. So your pH value is above 7, which means this guy would be basic. Again, no two answers on that. So just the pH, take a look at it, and you will see it is basic here. Any questions on that one there? Now, if we look at number 2, in the case of number 2, we have the OH minus concentration given to us. So in this particular case, we have 9.2 to the minus 2, it looks like. Now, again, here you cannot go directly into the pH, but because we have the OH minus, we can go into the POH, and that would be minus the log of the OH minus concentration. That's going to be minus the log of 9.2 times 10 to the minus 2. And that will get us a POH of 1.04. And in this particular case, we can again subtract 14, which is probably the easier move at this point to get to us to our pH. And our pH here would be 12.96. Again, at this point, we want to look at the pH value, and we see that the pH value is above 7, and that means that this solution should be basic. Question on those two calculations. Again, you could have used KW like we used before, and you should get pretty much the same answer. Any questions on those two? All right. We will skip this one since it's just subtracting. Let's try this one here, our part of the calculation. So we have the pH is 3.14. What is the H plus concentration? So take a second here and see if you can get that properly on your calculator. So remember that when we are given the pH, again, in the name, it tells you what you could get from it. You could get the H plus concentration, and that is the inverse log of the minus pH. So again, when you do that on your calculator, usually will pop a 10 and a caret. Negative 3.14 will get you 7.2 to the minus 4. And again, since this is a concentration, we would want molarity. So again, in terms of getting this part of it on most people's calculator, that's the shift or second button up there in the top left. That's the LOG button. That is the negative button, and that is 3.14 and the equal button. So On most people's calculator, that's sort of how you punch that in to get yourself to that. It won't give it to you probably in scientific notation. It obviously may give it to you. It looks something like this. You can, if you like I did, put it into scientific notation. So again, your calculator will probably spit it out to you in decimal form, and you can convert it to scientific notation. Question on that calculation there. Okay. Why don't you try one more here? The pOH is 5.67. What is the OH minus concentration? Okay, so basically it is the same calculation. So from the pOH, you could get the OH minus concentration, and that would be the inverse log of the minus pOH. Again, on your calculator, if you do it sort of properly, usually a 10 and a caret, minus 5.67, going to give us, I think what we see in there, 2.1 times 10 to the minus 6 molar. And let's just talk a little bit about sort of sig figs going backwards. This has 2 decimal places, which means this guy should end up with 2 significant figures. So you want to kind of go backwards the same way as we go forward. So if this had 2 significant figures, our pH or pOH would have 2 decimal places. Going backwards, we have 2 decimal places. We would actually end up with 2 sig figs on that case. Question on that calculation, again, punched in exactly the same way as we did the previous one. Okay. So those are important equations. Make sure you obviously know how to calculate them, and how to punch them in is most important. What I'm going to do is I'm going to skip these couple of examples here. We'll come back to it and talk about it later. But let's talk first about a buffer to finish up here, talking about sort of acids and bases and what a buffer is. A buffer is basically a solution that can resist changes to pH, even if you add a strong acid or a strong base to it. Now, people oftentimes think a buffer is a neutral solution, and it's not. A buffer could be at any pH you like. You can have an acidic buffer, basic buffer, neutral buffer. It just means whatever pH is at. So say we made a buffer at a pH of 4.5. If I add acid to it, it will stay around 4.5. If I add base to it, it will stay around 4.5. We will not see a giant jump in the pH if you add acid or base to it. So again, first off, it's not necessarily a neutral solution. It just means that it's able to resist changes in pH. It's able to do that because it contains a weak acid and a conjugate base, or a weak base and a conjugate acid, or the salt of a conjugate acid, or the salt of a conjugate base. And because a buffer has both of those things in there, it's able to prevent the pH from going really crazy. So let's just look really quick here at what happens if I add water. I'm sorry, if I add acid to water. Water is not a buffer. And if I add something like HCl, which is a strong acid, to water, it's going to 100% break apart into H plus and Cl minus. Now, in this case, in water, we just created a lot of free H plus. So the amount of H plus just went up, which means the pH is going to go down a lot. And we would expect the pH to jump a lot. So maybe the water started at a pH of 5 or 6. You add some acid, it goes all the way down like a pH of 1 or 2. A very big jump in the pH. Because we added a lot of H plus, the pH is related to that H plus, right? So because we added a lot of it, we will see a big jump in it. Now, if we added something like sodium hydroxide, which is a strong base, to a buffer, it would 100% break apart into sodium ion and OH minus ion. Now, we just made a lot of free OH minus. And if you remember, the H plus concentration and the OH minus concentration are tied to each other. If you make a lot of OH minus, the amount of H plus goes way down. And what that happens to the pH is it goes way up. So perhaps our water goes from a pH of 5 all the way up to like maybe a pH of 10 or something like that when you add the OH minus. So in water, which is not a buffer, it has no way to basically handle that when you add an acid or base to it. Now, if you take that same and add it to a buffer, like acetic acid, this is acetic acid, and sodium acetate. This is a weak acid, and this is his conjugate base, basically. So both of these guys are in that solution to begin with. So when we make this buffer, we have both of those things in the solution to begin with. So there's an acid part and there's a base part. So what happens when we add hydrochloric acid to our buffer is the hydrochloric acid will react with the base part of the buffer, and we'll get a double displacement reaction that will occur, and we will produce acetic acid and sodium chloride. So when we look at this side, when we add it to the buffer, we made acetic acid that was part of the buffer to begin with, so that's not going to mess up the pH. We made sodium chloride, which is a neutral salt. But more importantly, when we added that acid, we do not see any free H plus like we did when we added it to the water. So when we added the acid to the water, we made a ton of H plus that was free. Over here, when we added it to the buffer, we have no free H plus made, which means if we didn't make any more H plus, the concentration of H plus will remain relatively constant, and the pH will then remain relatively constant as well. So because we're able to keep the H plus concentration relatively constant, we will not have a big jump in the pH. It will move slowly a little bit in the acidic direction, but you won't see a giant jump in the pH because we basically maintain the H plus concentration. Same thing happens here. I know we're getting to the end. We're past the end, I think. But if we added the sodium hydroxide to that buffer, that's a base. It will react with the acid part of the buffer, which is acetic acid. And it will make sodium acetate, which is part of the buffer, and it will make water. So water is not going to affect the pH. The sodium acetate, which was part of the buffer, won't affect the pH. But just like with the acid, most importantly, what we don't see when we add the base to the buffer is we don't see any free OH minus. So when you do that to the buffer, no free OH minus. And because OH minus is related to H plus, the H plus concentration still remains relatively constant, and the pH remains relatively constant as well because of that. So ultimately, the way a buffer works is because it has an acid part and a base part. When you add acid or base to a buffer, it basically prevents the formation of free H plus, which would make the pH go way down. And it prevents the formation of free OH minus, which would make the pH go way up. And by preventing those guys from being formed, is able to maintain the H plus concentration it started at and essentially maintain its pH so you don't get giant jumps in pH. If you were monitoring it with a pH meter, for example, your pH of this solution maybe was 4.74, and you added some base to it, maybe it goes up to 4.84, 4.9. Not a very big jump, but it goes up a little bit, but it won't go from like a pH of 4 all the way up to like a pH of 12 if it's done correctly. So I know we're sort of at the end, so I will shut up right now and stop. So we will stop there today. A reminder again, exam on Wednesday. So just like last time, you'll have the entire lecture period to take it. We'll take it through proctoral and on Canvas, just like the last one. You'll have to upload, obviously, some work like the previous exam and all that kind of stuff. And so there will be no lecture on Wednesday. And then afterwards, obviously, you could get to a discussion or lab, depending on which one you have. And just like last time, I'm probably will open up a little bit early so you don't feel so rushed to get to lab and all that kind of stuff if you do have lab on Wednesday. Other than that, thank you for listening. If you're out, have a good rest of your day and week, I guess. And if you are discussion, we'll discuss in about 5 minutes or so you can get up and stretch. Make sure you put here if you haven't done so. And I will either see you in a bit or have a good week, I guess. I won't see, or maybe I can see you on discussion day. So I'll see you on Wednesday then, maybe.